Okay, clean up the board a little bit. Let's look at the equation for this circuit for the overall gain of this amplifier. So the nice thing about this, we can view this as a two-stage amplification process. We can say we have some gain of this initial stage, and we already knew what that was. The gain of the initial stage was 1 over Rg times Rg plus R3 plus R3. We can rewrite that as A1 is equal to 1 plus 2 R3 over Rg. And then we know the gain of the second stage. The second stage is going to be a standard difference amplifier. And we labeled our resistors to show that we have equivalent resistor values. So we know the gain of the second stage, A2, is going to be R2 over R1. And that allows us to look at the gain of the overall gain of the amplifier, A, which is going to be A1 times A2, the gain of the first stage times the gain of the second stage, which is going to be R2 over R1 times 1 plus 2R3 over Rg. So again, in practical amplifier designs, we're going to have some gain here with this R2 over R1. That's typically going to be built in internally to the amplifier. And then we're going to have some programmable gain here that can be determined by setting this value of Rg. So let's talk about changing the value of Rg. So we talked in the last video about you can use a separate value for Rg here. Sometimes what you can have is you'll have a circuit where there's some resistance built in, and it's designed to basically just have you add a potentiometer. So sometimes, especially if it's a system where you're going to want to have controllable gain, like controllable gain that's not set by a resistor, but set, being able to adjust it with a pot or something like that. That would be where you would add, where there might be some built-in gain to allow you to use a standard potentiometer in here. Or it might just be, you can just slap a standard potentiometer in there as the resistance. You have to be a little careful though with potentiometers, because potentiometers use as resistances in feedback circuits like this. This feedback circuit is, as you know, they're very sensitive to these values of resistances. So sometimes potentiometers are a little bit noisy. Sometimes you will get acoustic noise, vibration noise in potentiometers, just due to the fact that you have a resistance set by a mechanical connection. You don't actually have a chemical bond between the materials, you have a mechanical contact. And in lower quality potentiometers, that can sort of vary. Also, the materials that they're made out of potentiometers are often not quite as linear with temperature as other materials. In a very good instrumentation amplifier, not only would these resistor values all be balanced and trimmed from the factory, but they would also be designed internally to have compensation for changes in temperature. And they would be designed to limit aging effects. Sometimes, though, some manufacturers will say, there's no way to guarantee that these resistor values will stay the same, they will stay stable for the life, for forever. So sometimes what they will do is they will give you a little bit of access to R2. So sometimes they will instruct you to add your own potentiometer here and connect it to ground. So that is one method that is sometimes used, and this allows you to trim this. Why do we want to trim this? Why do we want to keep this stage of the amplifier balanced? So this is a review from a few lectures ago. I'll let you try to answer that question. That's right, the reason we want to keep it balanced is because balance is required to maintain that common mode rejection. So as the circuit gets out of balance, the biggest issue we face is the more out of balance this is, the more the common mode will start to propagate through to the output. And really we want to have that common mode as rejected as possible in this circuit. Okay. There's also, the book talks about this quite a bit, there's a lot of times where the designers, manufacturers of instrumentation amplifiers will give the user more access to the internals that allow them to do some nifty features to eliminate some unintended consequences of, for instance, transmitting a signal over a long distance or something like that. One option that they'll do a lot is they will give the user access to both of these nodes. Sense and R2. The user can then, whatever distance they need to have this signal travel, and I went way off the page here, so I'm going to scale it back here. Sorry, I went on a screen. So whatever distance this has to travel, we'll do a little, to show that this actually travels some great distance. The user is then responsible at their end of connecting this to ground and connecting these two signals together to provide their output signal. What's the advantage of doing this? The advantage of doing this is allowing you to connect this point of this resistor to your output signal, wherever that output signal is it allows this circuit overall to compensate for parasitic resistances or noise that might be injected into this. So it's a way to guarantee that the output voltage actually at the destination is correct. Because sometimes even if your output voltage coming out of your chip is correct, that doesn't mean it was correct all the way at its destination. This is one way that you can help improve that. You can help clean up any noise or any parasitic resistive effects that might have been created by having that long distance movement of an analog signal. Analog signals in general, we don't like to have them go very far because the longer they go, the more they pick up noise, the more they pick up undesirable resistances and capacitances and inductances. But this is one way that can help us clean that up. We can just sort of use the internals of this design to help make sure we have a nice, clean, coherent signal at the other end. As we've already talked about also, one of the main uses of this type of amplifier is quite often it's easy for us to have a signal represented as a differential value, but that signal will be riding on top of noise, either because of the design of a particular transducer that we're using. So a lot of transducers use a bridge configuration where any amount of noise that's coming on the voltage supply of that bridge will create a differential noise in the signal. So that's one benefit of this. Also, it's very easy for us to, or it's by doing different techniques like using coaxial cables or by twisting pairs, we can help minimize the noise that's created between two signals, but it's very difficult to minimize noise created in both of those signals as they travel a long distance, right? So in cases where there's a long wire, we can use this type of configuration to essentially subtract out the noise that's produced in a reference signal from our actual desired signal. We'll also talk about a little bit later, there are ways to get a differential signal. Like let's say we had a bridge amplifier that had a differential signal that was riding on top of some noise. And let's say that signal was being transmitted over a distance and it was also picking up noise by being transmitted over a distance. There's ways we can tweak this amplifier design to actually essentially subtract two signals. We can subtract the noise signal and then also look at the difference here. And actually, I guess I'll jump ahead and do that really quick because it's fairly easy to do. So if we wanted to do that, we could simply add another divider here. And add our guard signal that needs to be, add our trace that all it's doing is collecting noise, add it here, remove that signal difference, or have this be our sort of new reference signal reference, and then still get that differential signal. So that's one way we can tweak this. I'm not going to spend too much time talking about that. But it's just one thing to note. If you buy an instrumentation amplifier, and you see some of these features on here, if you see a sense pin, this is typically called a ref pin, I didn't label it. And actually we'll talk a little bit later about offsets as well. If you see some of these like guard or sense, reference, if you see these on the package, note that that instrumentation amplifier is capable of doing these different things. And so it's really important that you look at the data sheet. Make sure you're using it correctly. Also because quite often it will require an external connection between, say, sense and the output. Even if you're not really using it for its intended purpose, it still does require that connection. So always be sure if you're working with an exotic instrumentation amplifier to check these things. Okay, one of the downsides about this amplifier design is we have to pay for 3 op amps to do this. We have to pay for 3 op amps, and 2 of them have to really have high input impedance. So these 2 amplifiers, maybe they would be JFET input amplifiers. They could be a MOSFET input amplifiers. But we would definitely want these 2 to have really high input impedance. Having 3 amplifiers means we have to take up 3 times as much silicon in the chip that we're making this with. And so the question is there a way we can build an equivalent amplifier to this using fewer op amps? And there is. We can actually do this also using this is sort of the most elegant approach, but there are other approaches we can do we can do this same thing basically using 2 op amps instead of 3, and that's what we're going to go over next. So I will draw the dual op amp. Oops. I will draw the dual op amp circuit. So what are we doing here? So here we have again, the goal here is to build a difference amplifier which has a very high input impedance, very high input resistance. This is another way to do it. So in this case, we have an input. We have, what type of op amp is this? What op amp configuration is this? That's right, it's a non-inverting amplifier. And what type of op amp configuration is this? Also a non-inverting amplifier. So essentially what we have here is we have a non-inverting amplifier stage for this signal V1, which allows it to basically be buffered with still having high input resistance. And we also have this second stage, which is being buffered for V2, and it is taking that buffered V1 signal and taking the difference of it, right? So this would be a way of doing a difference amplifier configuration. And what we're doing here is by choosing this, essentially we have a gain value here, which is then reversed on this stage of the amplifier. So what we're going to have is we're going to sort of, whatever change we made, whatever sort of imbalance we created in our amplification of V1 over here, we can correct it over here. Okay. So, what is our overall transfer function for this? What is our overall system equation for this? So in the case where R3 over R4 equals R1 over R2, in the case where we maintain this ratio between these two, V out equals 1 plus R2 over R1 V2 minus V1. There's a problem you'll have in the homework that has you prove this, has you go through the process of verifying this. But this is something that's a good practice for you to do on your own. So this is something that you can do on your own. You can test this. You can verify that this works. And it's very good practice. It's not necessarily intuitive. This circuit is not necessarily that intuitive because what's happening is this V1 signal is propagating across both networks. The V2 signal is propagating across one network. So just keep that in mind when you're doing this analysis. But to make this expression true, we have to maintain this ratio of resistors. So I guess in this case, we're not saying they're equal to each other. We're not fully reversing what they're saying. Okay. Now, the downside of this, though, this is a dual operational amplifier. The downside is this does not have variable gain right now. So in this case, these resistor values would have to maintain this ratio. They would be built into the chip. We would not have access to them. What if we did want to take this same design? We've found a way to make a high input resistance operational amplifier with only 2 op amps. What if we wanted to add gain here? If we want to add gain, what we have to do is we do have to keep these exactly the same. So internally, these resistor values would have to stay the same. So we'd have to have R2, R1, R1, R2. Keep in mind it's the same but flipped here. But then we would add an extra resistance here. By putting this resistance here, it allows us to maintain our ratios as we did before, but still change this ratio, this equivalent ratio R1, R2. And for this circuit, and again, there's another problem that you'll do, and you can do it. It's good practice to do too, but it'll take up a little more time than would make this video feasible. If you want to derive this, it is one of the problems in the book, and I think it's one of the problems in one of our assignments. But the overall gain of this amplifier structure is going to be 1 plus R2 over R1 plus 2 R2 over RG. What's the downside of this? What makes this less ideal than in the previous case? This is highly nonlinear. So especially if this ratio R2 over R1 is not small, this becomes it's similar to what we had before, 2 over R2 over RG, but instead of having 1 plus this ratio, we now have 1 plus this component plus the ratio. So it can create a slightly more wonky gain curve, but the reality is it wasn't super clean to begin with. The old version wasn't super clean either. Ultimately, what you do is look up a table, and most manufacturers would have explicit values of gains that people would use. So it would say, if you want to have a gain of 1,000, use this value, 100, use this value, 10, use this value. So typically, they're pre-calculated for you, in which case it's not that big of a deal. Even having this extra term here doesn't really matter too much. So this is just another way to do this, slightly cheaper way to make a similar performing amplifier. The biggest question is, and we won't do the analysis here, the biggest question is, as always, what happens when this ratio slips a little bit? What happens if these resistor ratios start to slip? So that is always the question, and that's always the challenge for manufacturers who are making these. Sort of how reliably can they guarantee rejection of the common mode in their design? And it's something, if they can do a better job, they can sell their amplifier for more money. If they can make it more stable over time, they can sell their amplifier for more money. Sometimes that might mean they go to a 3 amplifier configuration. I would say probably 70% of the instrumentation amplifiers on the market, though, are going to use this sort of 2 amplifier connection to do what they do. So, okay. We are going to stop this video here and pick it up a little bit later.